Hello and welcome to Digital Futures tutorial session. Today we have pleasure to introduce Andrea Rossi and have tutorial on Grasshopper Wasp. Before we begin today's session, I would like to also inform our audience about our next session, which is tomorrow on architecture and philosophy, along with FIU on Judith Butler. And the panel will be held by Helen Runting and Emilia Jones. Uh, Without further ado, I would like to now introduce Andrea, and we are really grateful for him to take out the time for this session today. Andrea is an architectural researcher and computational designer. He is a doctoral candidate at Digital Design Unit at TU Darmstadt, as well as a research associate at Experimental and Digital Design and Construction Chair at the University of Kassel. His current focus is on discrete design, robotic fabrication, and bio-based materials for construction. He is a developer of the plugin Wasp, an open source Grasshopper plugin for discrete modeling. Previously, he's also worked at ETH Zurich and Politecnico di Milano. He has taught workshops on digital design tools, robotic fabrication in Italy, Germany, USA, and Israel. Welcome, Andrea, and the screen is all yours.
Thanks for the introduction. So I'm super happy to be here. So yeah, hi everyone. It's nice to see everyone here. It's gonna be quite fun, I hope. So the idea for today is to do a couple of things. So first, I'm gonna do a little bit of an introduction about the ideas and the concept behind Wasp and how Wasp came to be as a plugin, and also some of the ideas that are behind Wasp that go a little bit beyond just being about software. And then we're going to try to do a tutorial in which we're going to build a single tutorial file, which is going to build from the very basics of Wasp, like understanding what are the basic building blocks to work with Wasp. And then we're going to move from there all the way to try to build a relatively complex Wasp aggregation. So I'm going to give you some more details on that as we start with it. But for now, I'm going to start sharing my screen. And we can maybe get started with a little introduction about what Wasp is and why Wasp exists. So let's say I'm going to skip a little bit. This was a bit of a longer presentation, so we don't want to take too much time on it. But so I'm going to jump some parts of it. But just for you to understand a little where Wasp comes from. So Wasp kind of sits itself in a, let's say, debate that is probably existing since when architecture existed. And the fundamental idea is the debate whether architecture is built out of discrete elements, out of elements that are composed together, or whether architecture would be created more as a continuous mass that gets folded over itself over time again. And so we can see that in early history from where from one side we have classical architecture where everything is built out of individual elements that are composed in space versus some other types of architecture, in this case some churches in Ethiopia, in Lalibela, where the building is really carved of a single mass, and so it's actually not composed of elements in itself, but it's rather like one continuous mass. And what's interesting is that this debate between continuity and discreteness, if you want to call it, kind of exists all over architectural history. So you can see this tension in between, for example, Romanic architecture and Gothic architecture. And then when we come to today and you look a little bit at the impact of computational design tools and the research that emerged from the constructivism of the last 20 years, we see that we are very much leaning towards continuity. So we're very much leaning towards an idea that buildings are composed by these very complex continuous surfaces. Continuity is one of the fundamental aesthetic drivers that kind of is researched. And this is also something that kind of came to be defined by Patrick Schumacher with the term parametricism, which is this idea that we build architecture as a continuous variation along continuous domains that kind of articulates all these design tasks over them. Now, what I found interesting and what came a little bit to be in my research is this idea that despite the fact that we are looking at continuity as one of the fundamental paradigms of architecture today, the way in which we build buildings, the way in which they're fabricated and they're composed is still very much discrete and is still very much composed of individual elements that have to be combined in order to create then this continuity. And what we can say that this research that is kind of pushing in the direction of saying, well, if we can push additive manufacturing and 3D printing to this extreme of complex multi-material printing, we could kind of get into this world in which architecture can be materialized as a continuous object and not anymore as a composition of elements. However, if you look at what really 3D printing is and what it comes out of 3D printing, you see that there are quite a few issues with that. So we see that what we print, if we try and think at a building being completely printed in one single concrete block, we end up with a building that is highly customized and really hard to change. So what happens is that we end up with buildings that are super specific for one use, but are very hard to modify and adapt to another use. So in my research, I started looking a little bit at this idea of, could we think about additive manufacturing processes that are not continuous, but rather discrete, meaning that we can still work in an additive way, adding elements, but these additive processes, they are reversible, meaning that the blocks we use can be disassembled and reformed. And of course, if you want to talk about that, we have to talk about parts. And parts, of course, as we said, exist in architecture probably since when architecture started to be defined as such. But what's very interesting, if we look at modular architecture, and a lot of modular architecture examples, particularly, for example, in modernist times, we see that the way in which parts are defined in a building is that those parts are defined for their function. So particularly we define, for example, a basement block, we define floors, we define stairs, we define columns. And what's interesting is that each of these elements have very specific geometries that allows them to perform exclusively as one of those functions. So a column cannot easily become a floor cannot easily become a stair, and so on. And so we have this idea of very functionally differentiated parts that from one side constitutes the nature and the great achievement of modernist architecture, but at the same time constitutes one of its limits. And its limits in a sense that buildings tend to be extremely rigid, very hard to modify and to adapt. And that's exactly because since parts have very specific functions, they cannot be easily adapted to other uses. And now, this is kind of a bit of a longer discourse, but what's very interesting is that if you look at one of the fundamental tools that we use in design today, which is BIM, BIM borrows exactly this idea of functionally differentiated parts. And that's actually one of the reasons why often BIM software becomes very hard to design with. While it's extremely good to documenting a design object, it becomes very hard to use it for actual design processes that break the conventional idea of let's say functional differentiation. So if we want to talk about parts but not be constrained by this functional differentiation, we might have to look for parts and ideas of what parts can be somewhere else. And one example in which where this one could be looked for is the idea of a digital pixel. So if you think about a digital pixel is very much a point in space that by itself does not have any meaning, but rather assumes its meaning by combining its state, being a certain color, with the states of all the pixels next to it. So by default, a pixel is not a part of an eye or a part of a tree or something, but it becomes so by defining the relationship between itself and its parts. So the question a little bit that kind of underlines on my research and also then the development of Wasp is how we can move in architecture from the idea of functionally differentiated parts to the idea of generic parts, where we don't define anymore a column or a floor, but we rather have parts that create a column or a floor based on the way in which they're arranged in connection to the other parts they're working with. And What's interesting, I'm going to skip quite quickly over here, is that this concept exists already. And it's a concept that has been defined, the concept of digital materials, which have been developed at the Center for Bits and Atoms at MIT by the team of Neil Gershenfeld. And it's exactly this idea of a material that is composed of discrete elements. And those discrete elements can be combined in a finite number of ways. And obviously, the most common example you can think of for something like this is a Lego brick. So a Lego brick has its own pins, and those pins allows you to connect things in a finite number of ways, and each brick has its own position and cannot be connected, let's say, it halfway. And another good example of such a thing, of this idea of digital materials, are DNA and RNA chains. So there as well, we have a very finite number of bases that can connect in a specific finite number of ways. And by doing this, they allow to create sequences that have a very low error rate, and that they can be reproduced very easily because they really embed into themselves this specific grammar. And once again, when we talk about digital materials, we're talking about three different fundamental characteristics that define them. And the first one being programmability, the second one being reversibility, and the third one being reliability. And what does that mean? What does that mean when we talk about programmability? It means that positioning blocks in space is equal to fundamentally defining a programming sequence in space. So as things are discrete and they can be combined just in a certain number of ways, the way in which we connect things can be easily represented as a simple sequence of discrete decisions. And so that makes it very easy to represent a complex structure without the need of very complex geometric information behind it. And so we explored this with some of my students. And reversibility is, of course, a second very important characteristic, and was actually, for me, one of the starting point of the research. And it was this idea that if you are assembling parts which are discrete, which are generic, and which are connected with reversible joints, you can actually at any time disassemble them and reuse them for another assembly. So in this case, you see a very good example of this was a study done by the MIT team that developed the concept of digital materials, where they went on a hike using a set of parts that was used to build a bridge, build a little boat, and then build a tent as well. And again, with some of our students, we explored this idea in architecture on how you could create architecture that is custom adapted to the bodies of its users and the function they're performing by constantly reconfiguring the different elements that are there. And lastly, of course, is the idea of reliability, which means that if we break down architecture into discrete parts, we are all of a sudden reducing the possibility of error, because each part is just having a specific position in space. And so errors do not propagate, but they kind of get corrected as soon as we move to the next part. And so what that means for architecture is that it means that we can use, of course, very accurate machines to work with these parts, but we can also use very inaccurate machine, like in this case, a kid using an augmented reality headset being able to still assemble these parts, as all the assembly sequences are predefined by the geometry of the part itself. So, of course, these ideas have been borrowed by material engineering, and so by this field. And the question is, do they even exist in architecture? And of course they do. And already during the modernist times, we had some key figures like Konrad Wachsmann and Fritz Haller, and further on Yona Friedman and Moshe Safdie, which looked at the idea of how architecture could be retaught when thinking about discrete parts that are composed in space. And so in all these researches, it emerges this idea of working with generic parts rather than with specifically functional parts, and looking at how structures can be built in a really different ways without rigid hierarchies, but rather allowing more freedom in them. And more recently, these ideas have been brought to the light again, and became pretty prominent in the computational design discourse, thanks to two key figures, which are Gilles Retzin and Jose Sanchez, which explored again this idea of how architecture could be retaught as discrete parts, and what that would mean both for its functional application, but also for like a different aesthetic language. Now, while this interest for this thing kind of became more apparent over the last few, I would say 3-4 years, what I noticed is that there were a lot of discrete projects and ideas and approaches behind it, but there was a lack of tools and generalized approach to deal with this. And so that was the reason why Wasp came to be. And so Wasp came to be as a tool for Grasshopper to allow users without deep programming knowledge to explore the ideas of discrete assemblies. So the basic idea behind Wasp, and we're going to see it in practice today, it's quite simple. And the idea is that we are able through Wasp to define parts which are nothing else than closed geometries that have on certain faces planes which we will call connections, which are the locations where one element can be connected to it. And then what we do simply is, once we define all these parts, we write rules that say what can be connected to what. And once we have done that and we define all the possible rules within one system, we can run different types of algorithm that will compose these structures into larger aggregations. So what Wasp does in the back is also taking care a little bit of keeping things clean and making sure there's no collisions, making sure that all the grammars are respected, and so on. And see here, you can see some examples that have been created in like few days workshops by some of the students I had in the past. And you can see how it's very quickly possible to create these very large aggregations that would otherwise require a lot of time in being modeled. And then, of course, the next question, after we can define the internal logic and the connection and so on, is how do we control the final shape? And so the way in which we do that is using voxels. And so for the one of you who don't know what the concept of voxels exactly is, voxels are nothing else than pixels in three-dimensional space. So we have points in space that can store different values. And so what we can do with Wasp is we can create different kind of voxel fields. For example, in this case, we create a voxel field based on the distance of our voxel points from a curve. And then we can actually use an algorithm internally that will rebuild this voxel space using the parts that we defined in advance. And so we can do that, as we say, with distance values. We can do that with material densities, as in this case here with topology optimization. And then, like, what's interesting is that as soon as you have this toolkit, you can start looking for and exploring a variety of different ideas and concepts that have to do with this idea of building architecture that is not static, but it's rather reversible, and it's able to be adapted to specific conditions, being them landscape or historical sites, and so on. And so I started developing Wasp at the Digital Design Unit at TU Darmstadt, and soon after we had the first design studios and research and seminars using Wasp, we immediately thought that it would make a lot of sense not only to keep this tool as a closed tool within our team, but rather share it into a larger network in order to kind of increase the debate and also the research into these topics. And so what happened is that very quickly we had a lot of projects popping up. In this case, some work that was done at the University of Texas or at the AA Visiting School New York, which was run by Marvin Bratke and Paul Bart and Ramon Weber. Or once again, there was some work done at the University of Innsbruck and the Institute for Structural Design. And so what's interesting is that what we did afterwards is we started trying to find a way to track all these different projects. And so that was done thanks to social media using an Instagram account. And so using both the Instagram account itself and then like the hashtag GHWasp, it was actually possible to start collecting this wide variety of projects, which showed the potential of not keeping tools closed and hidden within research unit, but rather sharing them with a wider community. And more recently, I also started a Discord community that allows everyone to keep track of, share their work, ask questions, propose new ideas for the development. And here you have a QR code, and you're of course all welcome, if you're not there already, to join Discord. And then not only Wasp was shared as was shared with the whole community, but was particularly shared as an open source tool. And so what that means is that the code of Wasp is free and it's available for everyone to use, to open, to look. And it's an interesting code to look for if you want to, for example, learn a bit more about programming in Python, as well as if you want to, for example, start adapting Wasp to specific uses that Wasp was not initially taught for. And this is a little bit what happened over the last few years. There have been quite a few projects that emerged as adaptations or built on top of Wasp. And one of them was, for example, Project Disco, which if you don't know, I would recommend you to check out. The website is, I think, projectdisco.com or .net, but you can just find it if you search Project Disco Wasp. And this is a very interesting tool because it's virtual reality game-like environment, which allows multiple people to collaborate in building structures using Wasp. And you can look it out. It's been developed by Jan-Philipp Drude, and he has some very nice tutorials about how to use it and how to set it up, and also how to connect it with Wasp. As well as this project that was developed at the University of Applied Arts in Vienna by Lukas Allner and Daniela Krönert, which they were looking for a way to create aggregations, not of parts that were all the same, but of parts that were all unique, and that these parts were 3D scanned wood branches. And what was very interesting was that with them, they were able also then in collaboration with me to develop a custom branch of Wasp that was called Conceptual Joining Wasp, that allowed to represent these more complex structures and also find a way to optimize them in a certain way to then make them buildable. And or as well, like a project like Wasp++ that was developed by Blake Egeman at the Illinois Institute of Technology, which again was a tool that was built on top of Wasp to provide Wasp with some of missing functionalities. And so what was very interesting is that it's really this idea of that by opening up the code and allowing that to be used by different people, different researchers, different computational designers, and so on, it became possible to think Wasp not anymore as a single closed tool, but more as a glue that would allow to link together a variety of different projects. And more recently, and that's something that it's in progress right now, I've been looking more into the possibility of creating a data language that exists behind Wasp that allows to exchange Wasp geometries in between different files. But then I hope pretty soon also potentially to bring Wasp to other softwares rather than Grasshopper itself. And so what's very interesting is that if we have this built data representation in the back, we can very easily translate it to a variety of different tools and technologies, ranging from robotic arms to augmented realities processes, as well as kind of exchange between different softwares. In this case, you see a studio that I was teaching with Sajay Bhushan and Johannes Megens in Innsbruck, where we connected Wasp and Grasshopper together with Maya in order to create more complex geometries in between the two softwares. So we were able to first generate the organizational structure using Wasp and Grasshopper, and then bring this to Maya and then populate it with more complex structures. And lastly, and I'm going to really run quickly here because I took already quite a lot of time with this presentation. Nope. Okay. Is the idea of open production. And so this is a work that has been done by a student of mine, that is Felix Dannecker. And the possibility of that if we can build architecture out of these very small discrete parts, we can also reimagine production, not anymore as being a production that is done on site with very large machines, but rather production that could be done by unskilled users using very small machine. And so the idea here was to produce 3D printed cutting guides that would allow using simple woodworking tools to create very complex structures. And so there was a little bit this idea of exploring that and kind of creating the structures. And then also we did a competition for a playground that could be built by its users without the need of any construction company being involved. And so through this presentation that was hopefully not too messy and not too fast, I just wanted to show you a little bit this idea that Wasp as a tool, it's a software tool that allows you to do certain things, but beyond that, it's a tool that aims at looking at architecture in a more open and accessible way, and trying to do that both at the level of design, at the level of production, and at the level of use. So as I said, Wasp is an open source tool. So it's developed by me and pretty much in my free time. So I'm currently trying to make space for having more time and more energies to develop a Wasp. And for this, I recently launched a pattern page. So if you're interested and you want to support Wasp, you can sign up. You can support Wasp however you can, and you can get also some nice goodies like some Wasp stickers, and also you can get access to some more specific tutorial that are not available outside. So I guess that was it for today. I'm not sure if we should do questions now or we'd rather do that at the end. I guess we do that at the end, yeah?
Yes, yeah.
Okay, so if you have any questions, you can keep them for the end, or if you don't manage, as you can see here are all my contacts. So feel free to, or jump on the Discord chat and so on, and just ask anything you have. All right. So now that we went through a little bit the ideas behind, I just wanted to make sure that you all have the zip file that was posted in the chat. Maybe I'll post it once.
Can you please resend it? Yeah.
Yeah, I'll send it once again. So yeah, so you have a zip file there. So I'll assume that you all have Wasp installed and set up. And if not, please do so while I am going to do. So what we're going to do today, I'm going to show you a little teaser. We're going to try to work on an aggregation that is composed of, let's say, prototypical residential units, if you want. And what we want to look at specifically is how we can go from something very simple, like just some very simple blocks, to something that has much more detail, like you can see here, where we have like much more complex geometries, some ideas of facade, and also we have some specific elements, like in this case, for example, these balconies that are controlled from appearing just in certain locations in the aggregation. So it's going to be quite a long tutorial. So if you get lost at any time, in the zip file that I sent you, you'll find the finished file, but then you find also 6 steps. And if at any time you get lost or think, I'm going to try to refer you back to those steps. So whenever we reach the point where we are done with one of those, I'm going to just tell you so that you can just follow up and catch up. So if you get lost, don't panic. Just wait a little bit, and at some point I'm going to tell you, okay, now we are at step 1, and you can just open that file and come back to it. All right. So if you all have the files now, what I would ask you kindly is to open the Rhino file that you have here, and you have it in both versions for Rhino 6 and 7 or for Rhino 5. And so when you open that file, it's going to be empty. But actually, if you go in the layers, you might want to go and turn on the block number 1 layer. And you'll see that we actually have a little box. So now this is going to be our first very, very simple part that we're going to work with. And so what we're going to do now is we're going to go through the very basics of Wasp and how we can build an aggregation and define the rules for such a part. All right. So hope it's all clear. So what we're going to do is we're gonna start in our Rhino in our Grasshopper file, and we're gonna start by importing our block geometry. So we're gonna create a geometry block component. We're gonna right-click on it, set one geometry, and we're gonna select our block. So just for you to keep track, what we are trying to do now is we are trying to build our part. So we're gonna do 3 steps. We're gonna build our part, which is our little block with the way in which it connects to other parts. We're gonna then define the rules that allow this block to connect to other blocks. And lastly, we are gonna be aggregating them and creating a structure with them. So as I said, the first thing we wanna do is we're gonna use a geometry, and that's gonna be our geometry of our component. And then let's go on, and if you go on the Wasp tab and you go under parts, we can get a Wasp advanced part. Now, for the first thing we're going to do today, you could also use a basic part, but you're going to see later that we're going to add some. Oh, sorry. Yeah, I can share the file again.
Yeah, I'll share. Andrea, you can go ahead. I'll share.
Okay.
Thanks.
Cool. So yeah. So as we said, so we're going to use the advanced part because we're going to do some extra things later during the tutorial. So if you bring in this, the first 3 inputs that you see on this component are actually the only 3 ones that you really need for this to run. So we need to give our part a name. We need to give it a geometry. And we need to give it a series of connections, which is these planes where things can be connected to it. So for the name, we will need to create a panel. And there is a quicker way to create a panel, and that is that you can just type inverted commas. So like this, 2 inverted commas. And then you can just type what you want to type. And what I'm going to name this part is block 1. So be careful, Wasp names cannot have spaces, underscores, or weird characters. And that's because it can cause problems in the calculation of the rules. So I'm going to create my panel here with block 1. And I'm going to connect that to name. I'm going to take my geometry, and I'm going to connect it to the geometry tab. And now the last thing we have to do is we have to specify the connections. And so you'll see that on our block here, we have a series of points and a series of straight lines. And so this is the information that we're going to use to create our connection. So, and you understand that the reason why we need that is that if you just specify a point gives you an information about a position where 2 elements need to connect, but it doesn't tell you anything about the orientation because they could be connected at any angle. So that is why we create this second line, which allows you to specify not only the point, but also the exact position where that is. So we're going to create a point component. And now, just bear with me. It's really important that you keep in mind the exact sequence in which you select the points. So I'm going to right-click, set multiple points. And I'm going to pick 1, 2, 3, and 4. So just the 4 points on the side for now. So we are not taking top and bottom. Then I'm going to press enter. And if you want to make sure that you selected them in the right order, what you can do is you can create another component that is called point list. And we can connect our point to P. And then we can put a slider with, let's say, 1 in value to it. And this is now going to show you numbers that show you the exact order in which these points are connected inside this component. So that's the order in which those are stored in there. So now that we know the exact order, what we are going to do is we're going to go and get a curve component. We're going to right-click, set multiple curves, and select the 4 curves that are connected to our points in the same order. It's going to be 1, 0, 1, 2, and 3. And we press enter. So now that we have our position points and our orientations, we can go on and create our connection planes. To do that, we are going to go to the Wasp tab, and we're going to go to Elements. And we're going to get the very first component that is called Connection from Direction. So we're going to bring this in. We are going to connect our geometry to geometry. Our center, connection centers from our points. And for our up direction, we're going to use our curves. On each of the faces, you get now a plane that shows you the connection plane that we created now. Now, it might be that your plane looks much bigger or much smaller than mine, and you can just adjust the size by going to Display, Preview Plane Size, and change this number. So if, for example, I want them to be a bit smaller, you can change this to 2. And what we also want to do is we don't want to only create those connections, but we also want to assign them a type. And now the reason why you're getting a type is that what we can do is we can now say that all these connections are of the type side because they are on the sides of our box. And we can then use this information to create the rules of how things can be aggregated. So I'm going to once again create a panel, and I'm going to type in all caps side, and I'm going to use this as the type of my connection. So now I created my connection, which right now does not have an ID, and they are all of type side. Okay. Now we want to create again 2 more connections in order to store our top connections and our bottom connections. Yeah. So we're going to come a bit down in our file, and we're going to just repeat the same process. So we're going to create a point component. I'm going to right click, set 1 point. I'm going to pick the bottom point in my part. And I'm going to also create a curve component. Right click, set 1 curve, and then select the curve that is associated with the bottom point. So you see I have a point and my curve that are at the bottom of my box. So I'm going to then create another connection from direction. I'm going to again, the geometry is going to always be my box geometry. It is at the top. For the center, I'm going to use my point. And for the up vector, I'm going to use my curve. So you can see now that we have our plane that has been created at the bottom of my plane. And now, since this is at the bottom, we can also assign it a type, and the type will be bottom. So now we're nearly done. We just have one more step, and the last step is to create the top connection. So once again, we repeat the same process. Create a point, right click, set one point, and pick my top point. Create a curve. Set one curve, and pick my top curve. And now what we can do is we can create once again connection from direction. Again, our geometry will always be our top geometry, so our box up there. Our point is going to be our center, and our up vector is going to be our up. And so here we have our up plane on top here. And so since this is on top, we're going to assign it also a type, and the type is going to be top. So nice. So now we have all our connections. So my side connections, my bottom connections, and my top connection. All I'm going to do is I'm going to merge them together. So connection, connection, and connection. And now I'm going to take my connections that I created all together here and plug them in my connection tab in the part. So now here you can see we are done building our part. So what we've done is we defined the geometry for the part. We gave it a name, which is block 1. And then we created a series of connections that we are going to define where things can connect. If you got lost in this process because there was a lot of Rhino clicking and so on, you can just go to the workshop files, and you can just open the Wasp tutorial step 1, and you're going to have exactly the same that we have here. So if any of you got lost, just open that file now, and you can work from there. So for the connections on top and bottom, the reason why we're separating them is we're going to see that in a moment. And it's because we want to define different rules of how things can be connected. So if you think that this could be, let's say, a housing unit, if you would have bottom and top in the same group, what could happen is that the bottom could connect to the bottom. And so what happened is that you would have one unit here, and then the second unit would just end up being on top of it. So that is why we want to keep them separate, so that we can say that the top can connect to the bottom and the bottom to the top, but let's say we cannot connect top to top or bottom to bottom, because then things would be flipping. So as I said, you can be here, or if you got lost, just open the Wasp tutorial step 1, and you're going to be in the same place. So now that we have our part defined, we're going to go on and create an aggregation with it. So as we said, after defining the part, the next thing that we need to do is we need to define the rules for how things can be connected. So I'm going to be moving a bit further in the file, and I'm going to be going to rules, and I'm going to take a component that is called rules generator. Now, in Wasp, you can write rules in a variety of ways. You can write them individually. So writing, let's say, this connection with this connection with this connection, and so on. You can generate them from an existing aggregation, and there's a lot of different ways to do that. You can check my YouTube channel. There's quite a few videos explaining you how to create rules. But for now, we're going to use a rule generator because it's the quickest way to do that. So what the rule generator does is it's simply taking all the parts and generating all the possible rules in between them. And we're going to start with all the possible rules, and then we're going to see how to control them a little bit. So I'm going to take my part that I created, my block 1, and I'm going to connect it to the part input. And if you hover your mouse on the R output, you'll see that this automatically created 36 possible aggregation rules, which are all the possible combination of each part with each other part. So in this case, we have just one part, but it's still, since we have 6 connections, we have 6 multiplied by 6, 36 possibilities for them to connect to each other. So now that we have our part, we have our rule, we can go on and create our aggregation. So as I was showing in the presentation, in Wasp, you have 2 different types of aggregation, or actually 3, but let's say the main one that are mostly used are 2. And those are stochastic aggregations and field-driven aggregation. Now, stochastic aggregations is an aggregation process that it's, by the definition, stochastic is, it's another way of saying random, which means that the way in which things are allowed to connect to each other is based on the rules we give, but then the way in which the aggregation is actually built is by just simply repeating those rules one after the other one in a complete random process. So at every step, I pick a new part, I pick a new rule, and I keep growing in that way. Field-driven aggregations, we are not going to see them today. I have quite a few videos on YouTube as well if you want to look more into that. But they instead use what I was showing in the presentation. So they use these voxel fields that are used as drivers to control how the aggregation is built. So in this case, for simplicity, what we're going to be looking at is we're going to be looking at stochastic aggregation. So I'm going to go to the aggregation tab in Wasp, and I'm going to go to stochastic aggregation. So we're going to start with the parts that we want to aggregate. And that's going to be our part here. And then what we want to do is we want to add, we need to specify if we have any previous aggregation. So for example, if you had already built a model somewhere else and you want to grow that further, you could plug it in here. For now, we don't want to do that. So we're just going to leave that empty. The third input is one of the most important ones, which is how many parts we want in our aggregation. And I'm going to start with 120. We need to say what are the aggregation rules we want to work with. And those are going to be our Wasp, our rules that we created from the rule generator. And we're going to connect that to rules. And then we don't really need any of the others for now. The only extra input that we need is the reset input. So we're going to create a button. Then we're going to connect to reset. And the reason why we need this is that Wasp is Wasp works with persistent data, which means that once we create an aggregation, and let's say we create 100 parts, if we say to now create an aggregation with 200 parts, the first 100 parts will stay the same. And we just have 100 more parts being added on top of those. And if you instead would want to create like 200 completely new parts, that's where you can use the reset button to tell Wasp to recreate a completely new aggregation. Now, you might not see anything right now, but if you hover your mouse over parts out, you might see that you actually already have 120 parts. So the algorithm has been already computing, and it has been already creating an aggregation with 120 parts. Now, obviously, we don't just want to know that this has been created, but we want to, of course, see it as well. And so for us to see that, what we want to do is we can go to parts. And we're going to get a component that is called getPartGeometry. And we're going to go and connect our part out to part. And you see that effectively what we have been doing is we've been creating this aggregation of our boxes. Now we might want to visualize this a little bit better. And so we can create a custom preview. And we could give it a color with a swatch. So as you can see here, what we have is we have a structure that is composed by aggregating our cubes in all their different connections in order to create this complex structure. And as I was telling you, if you want to create a different structure, you can just go and press the reset button. And every time you click the reset button, you get a new structure created. Also, once you created a structure, you can always go and grab the slider and drag it up to add more parts. So it should be, particularly with such a simple geometry, should be quite stable and relatively fast with up to a few thousand geometries. After that, it might become a little bit laggy and kind of take a bit of time to calculate. But we can see here. Now, I would suggest you not to have too crazy numbers now, because we're going to be adding quite a bit of complexity to the aggregation in the next steps. And so like stay in the order of, let's say, 1 to 200 parts, because we're going to add a lot of detail. And that might just make everything very slow. So I hope everyone is here. If you got lost during this step, you can just open now the step 2 file. And this is going to be exactly the same of where we are right now. So now we have our aggregation. And we have an aggregation that has just one part. So what we might want to do right now is we want to go and, for example, create a second part. So we're going to see how we can control an aggregation that has more than one part. But even before that, what we might want to do is we might want to add a little bit of control on this aggregation. So you can see that right now the aggregation is an absolute mess. And the reason for that is that when we use our rule generator, we allowed everything to connect to everything. So fundamentally, we didn't care about the rules, the typologies that we created here. So we said that certain parts are of type side, certain parts are of type bottom, certain parts are of type top. So what we might want to do is we want to now use the rule grammar to define a way in which different types of connections are allowed to connect or not connect to each other. So what we're going to do is we're going to create a panel near our rule generator. And we are going to right click and uncheck multi-line data. So then now every single line we write in the panel will create a separate data entry. And so we're going to start by writing our first rule. And our first rule is that if you want to, it's going to be that the sides can connect to each other. So we're going to say that the connections of type side, so we're going to type the name of the connection type, which is side. And then we're going to type a larger than symbol that acts as a sort of an arrow. And then we're going to type side on the other side as well. Now, just make sure that you're typing with the correct caps. So if you wrote side here in all caps, this should be all caps too. And so if we now connect this to our grammar, you'll see that what we get here is not anymore 36 rules, but just 16, because those are just a combination of the side connections. And if we also go and now reset the aggregation, you see that our aggregation is now two-dimensional. And the reason is that we said that the only connection types that are allowed are the one between side connections. And since those are all oriented in the same way and they just grow next to each other, our aggregation becomes two-dimensional. And so if I grow it more, it's going to still stay two-dimensional. So now, nice, but of course we have control, but what we want to also do is we want to grow in height. And what's important is that we're going to grow up, but not down. So if you want to grow up but not down, that means that we're going to say that we're going to connect from the connection top. We're going to add a connection bottom and just put it on top of it. And then it's going to be again. So I have bottom, and then I have top, bottom, top, and kind of grow up. So I'm going to double click in my panel again. I'm going to go to the next line, and I'm going to write top, which is my connection type for the top block. And then I'm going to type a larger than, and then bottom. So be careful, please, not to have any spaces in these things. Otherwise, it's not going to be recognized. And if I now check this one, you see that I have my aggregation that becomes three-dimensional. But you see that by controlling this, we're making sure that all our blocks, let's say they stay in the correct orientation, so they're not flipping vertically or something like that. So I hope this is working for everyone. If you got lost, now it's when you can actually go to step 2. I had forgot this little part. So if you got lost, just open the step 2 file, and you will find this same structure. So as we do not have a lot of time today, now what we want to do as a next step is we want to add another part to the aggregation. But since we don't have too much time today, what I suggest is that we just move on and all together open the file step 3. So I'm going to do the same. So I'm going to go on and get my step 3 file. And so now you'll see that the step 3 file is exactly the same. It has an exactly same part, which is our second part. If you want to see that, you can turn on the block 2 layer in Rhino. And so you'll see that the block 2 part is this block that has an angle in the middle, and it has more connections. And so what you'll notice is that we structured the connections in the same exact way. So we have a type side, a type bottom, and a type top. And so what that means is that automatically, as soon as we do that, we are then able to use the same exact rule grammar that we defined to create an aggregation of multiple parts. So you'll notice also that we have another input here on our rule generator. And what is inside this rule generator is it's the possibility of defining if a part is allowed to connect to itself or not. So if I would go, for example, and you see now that I have 100 rules, which are all the possible combination between these two parts, given this grammar. If I now go and toggle this to false and reset, now you see that the aggregation has this constant alternation between part of one type or of another type. And the reason for that is that we are able to do that because we said that here a part is not allowed to connect to itself. And so like it's always going to be one red part, one yellow, one red. Then I'm going to turn this to true again. And now you'll see that also something that has been added is before extracting the part geometry here, we actually added a filter. And so this component is called filter parts by name. And what this component allows us to do is it allows us to filter the parts given their type. So now we have two parts, and one is called block 1, the other one is called block 2. And so we can just filter them out and give them a different color. So now that we have done that, we have our new part already embedded. What we want to do next is we now want to try and control the proportions between the parts. So this is a question that came up very often. So let's imagine that we are building, of course, this is very abstract, but let's just imagine that what we're trying to create now here is a residential aggregation. And so these two blocks are two different types of flats. And so when you try to create this structure, you might have different amounts of each of those flats that you might want to create. So for example, you want to have, let's say 20% of the block 1 types and 80% of the block 2. So the question is, how do you control that? And the way in which you control that is through a component that is one of the latest additions to Wasp. And this component is called part catalog. So what a part catalog is a component that allows you to define the amounts of each parts that you want to allow in your aggregation. And we will see it allows you also to control how this is defined. So what we're going to do is we're going to go to our aggregation here. And we're going to create a new component that you can find in the parts menu that is called the parts catalog. And so we're going to plug it here. And so what we need to specify is we need to first of all specify the parts that are in our aggregation. And that's going to come from our merge component that we have here. And then we need to specify the amounts of parts that we want for each aggregation. So what we're going to do is we're going to create a merge component. I'm going to say, as I said, that I want 20% of block type 1 and 80% of block type 2. We can now take these numbers. So now it's really important. Right now, we know we have two parts and we have these two numbers. So it's really important that you specify one number for each part type you have. If you have a different number of amounts and parts, you're going to get an error. So if I now take my merge and plug it in number, you see that I created a part catalog that allows me to create 20% of block 1 and 80% of block 2. So if I now take my catalog and plug it into the catalog input on my aggregation, when I go and reset, you actually notice that my aggregation effectively has a lot of yellow parts and very few red parts. If I would go and, for example, invert the numbers, I'm going to reset, you see that I have the opposite. So now I have a lot of red parts and very few yellow parts. So one thing that we can also do is we can also use another input that is called lim. And this input is defining whether this catalog is limited or not. So by default, the catalog is not limited. That means that the numbers we specify here, they just define the proportions that we would like to have in the final aggregation between between block 1 and block 2. If we instead set limited to true, what that means is that once the algorithm has created 80 parts of type block 1 and 20 parts of type block 2, the algorithm of aggregation will simply stop because the catalog has been exhausted. So if I'm going to create a toggle, double click to set it to true and connect it to limited. If I go and reset now, you see that my aggregation will turn orange. And if I go and check what happened in there, it's going to tell me that it could not place 20 parts. And so the reason why 20 parts could not be placed was that because since the catalog is limited, the sum of these two elements, of these two numbers here, is the maximum number of parts that can be created. So if, for example, I would set this one to 10, and I would go and reset, you'll see that in this case, I'm going to be told that it could not place 90 parts. And the reason for that is, again, since the catalog is limited, it's not possible to go beyond the total number of these two. So I'm going to now make my catalog non-limited again so that we can create more. So I'm going to make limited to false and just click. And now I have my aggregation where I can control a bit more. Not exactly the number, but the proportions. The last input, which is the adaptive input, is not really important when you're using stochastic aggregations, but it's normally useful when you're doing a field-driven aggregation. And the reason why it's useful is because what this does is it's adapting the probability of one part being placed versus another one based on a number of parts that are already placed in the aggregation. No, it doesn't override it, but yeah, so let's say the rules, and I'm reading a question that if the self-connection is false. So that's not overriding it, but what happens is that, so when you say that self P is on false, meaning that one part cannot connect to itself, what happens automatically is that you end up blocking the aggregation, because if one part always needs the next part to be placed, let's say if I have 10 of part A and 50 of part B, once I place 10 of part A, I'm not able anymore to place any part A because I reached the limit of the catalog. And I have no way to place any part B anymore because there is no free part A. So that's something that it's always important to kind of balance out between the rules and the catalog. Because what can happen is that if you don't have the rules that allow the catalog to be executed, then what happens is that automatically they block each other. So they don't override themselves, so they're independent. But of course, if the rules do not allow certain things to happen, then the catalog might not be completed because that's just like a, let's say, grammar limitation inside the system. Cool. Yeah. So here you can see, and that's quite nice because what you can really do very easily with this one is you can now come and control your aggregation. It's not going to be super accurate, meaning that it's not going to be exactly an super exact proportion because it just defines a probability of a part being placed. So this probability will then be combined with the probability determined by the rules. And so if, for example, you have many more rules that allow to place one part versus another one, you might get some difference between the proportions that you set here and the output proportions that you get there. So it's not exact science. If you have very large differences, it might be useful to set the adaptive limit to true, because that's going to kind of lower the probability as more parts are placed of a certain type. So I hope you could follow till here. So if it's all good, you can just keep following. If you lost something in this last step, you can just open now step 4, and we're going to be at the same place. So what we want to do now is we're going to do 2 more things. And those 2 things are, we're going to first try to address one structural problem of our aggregation. And the problem is that if you look at your aggregation right now, there's a lot of flying stuff. Yeah. So what we can see is that there are very many parts that don't have anything underneath them. And so what we want to do is we want to have a way to control this somehow. And specifically, we want to have a way to tell to the aggregation what should be supported. So what we want to do is we want to have a way to tell that certain location on our block should be supported. Otherwise, the aggregation itself would not be allowed to be placed. So to do that, we need to go back to our Rhino for a second. And so what we're going to do is we're going to go to the Grasshopper up here to the toolbar here. And we're going to click on this button with the black eye. And so what this does is for a second, it disables the Grasshopper preview. So if we go to Rhino now, and we're going to go to our layer tab. And for both our parts, we're going to turn on the supports layer. And you see what this is. So you see that both parts have 2 red lines which cut through the part. And what these red lines represent is they represent some sort of a support. So what we can do with Wasp then is we can say that these lines have to intersect with another part. Otherwise, the part is not allowed to be placed. And so we could go and say that both of them need to be supported, or that even just one of them is enough for the aggregation to exist. So we're going to start setting that up for our first part. So we're going to go here underneath our part 1, so our block 1. And we're going to create a curve component. We're going to right-click, set multiple curves. And we're going to select our 2 red curves for our block 1. And we're going to press enter. So what we're going to do then is we're going to create a list item. Connect our curves to it. And then we're going to zoom in and click on the little plus that it appears when you zoom in very much in order to add a second input. So what we have here is on the first input, we have the first curve. On the first output, sorry, we have the first curve. And on the second output, we have the second curve. So we have these 2 curves that come out at different places. So now that we have our 2 curves, we can create 2 different supports. So we can go on and we can go to constraints and we can get a Wasp support. And we can connect. So now we have to decide what we want to do. So we have 2 options. Option 1 is we can say that both of them have to be supported at the same time for this block to be placed. And now I would not recommend to do that because the aggregation will become extremely constrained and it's going to be very hard to place anything. So if you would want both of them to be supported, what you will do is you will plug both the inputs to the direction tab. What I'm going to do instead is I'm going to plug just one of them. And I'm gonna then copy paste the same component and connect instead the second one. So what's the difference? So if both curves would be, for example, here, like in this case, so if I would connect both of them there, this support component will say that both these lines have to be supported at the same time for this element to be placed. If I instead create two separate support components, one for one line and one for the other line, we are saying that I'm creating two separate supports, and it's enough that one of these two supports is supported for the part to be placed. So it's enough that either this is supported or this is supported. And that's what we want. So what we're going to do is I'm going to then create a merge component, connect my supports together. And I'm going to then take my merge and bring it up to the part in the support input. We then need to do the same for our second part. So we're going to go down to the second block 2. And we're going to just do the same. We're going to create a curve component. We're going to right-click, set multiple curves. And I'm going to go and select my two curves here and press enter. And again, I'm going to create a list item. I'm going to zoom in, add the second one. And then I'm going to create, again, two supports, one for each. And finally merge. And once I built exactly the same, so where I have my two curves there, my list item, my supports, and I merge them, I can take them and plug them in the support input of my component. Okay, now that we're done setting up our supports, we can go back to the Grasshopper tab toolbar here and click again on the red button here so that we can turn the preview on. And we can now go to our aggregation and reset it. And what you'll see is that it's not working. So you see that our components are still flying everywhere and our supports are not taken into consideration. Why our supports are not taken into consideration? The reason why our supports are not considered is because we did not activate them yet. So the way in which we can activate the supports is we need to change the aggregation mode. So if you go to the aggregation component, you see that when you have a mode input and if you hover over it, you see that there's 4 different possible modes that you could work with. So by default, Wasp uses mode 0. And mode 0 doesn't matter how many constraints you set on a part, those constraints will be ignored. We then have mode 1, which is the mode in which only local constraints are checked. Mode 2, which is the mode in which only global constraints are checked. And global constraints are things that you set at the level of the whole aggregation. And mode 3 is all the constraints are checked. So in our case, we have set some supports. And what supports is they are local constraints. And so what we need to do is we need to create a slider, set it to 1, and plug it to the mode input. If you now go and reset your aggregation, you see that the shape of your aggregation is changing pretty dramatically. And the reason for that is that now our constraints are being considered. And so parts are placed only if at least one of their two sides is supported by another part. And so that is why we get this kind of tree-like aggregation. Yep. So you see how by using this, we can automatically check the way which is our aggregation is, let's say, relatively stable, at least at the local level. Of course, this is no structural analysis of sort. It's just a way to specify geometric organizations that would make sense at the local level in order to create something that would be structurally stable. But again, like, of course, if you keep cantilevering, at some point, this whole thing will collapse. So please don't take this as any solid or valid structural simulation system, but it's just a way for you to kind of define a set of geometric configuration between the parts that would create stable connections, at least at the local level. So I hope everyone could follow till here. So we now have our aggregation with our two parts, with our part catalog that allows us to control how many of each we have, and with our supports that now allow us to control where we are. If any of you got lost, you can now open step 5, and you're going to be back with us. If you go and open now step 5, you're going to be at the same place with us. Now, the last thing that we want to do today is we want to look a little bit how we can make our aggregation looks a little bit nicer. Now, of course, whenever you work with an aggregation, you want to work as much as possible with very simple and very clean geometries. And that's simply because, particularly if you want to create aggregation with a lot of elements, the simpler the geometry, the faster the script is going to run. However, it's also important to think that at some point, you might also want to add more complexity to your aggregation. So for example, as we said, if we imagine that these elements are actually housing blocks of some sort of, like, let's say, rooms of some sort of a structure, you can, of course, imagine that this has to have a certain character. So it's going to have a floor, it's going to have a ceiling, it's going to have some walls, openings, and so on. So what we're going to see now is how to use Wasp attributes to store this kind of information within the part. And this information will not be calculated during aggregation, so it's not going to slow down the algorithm much. But it then allows you, after aggregation, to visualize this geometry and have a much better looking aggregation. So to do that, we have once again to go back to Rhino. And so what we need to do is we need to turn our Grasshopper preview off in the toolbar with clicking on the black eye. And we're going to go, and I'm going to go to my block 1, and I'm going to turn on the skeleton attribute component. And you'll see that what you have in there is you have a bit, I can maybe turn my ghosted view on. So we have, if I just hide the box, we have a little kind of cabin-like geometry. So there's some rounding. So it's nothing like, don't judge me on the design, but it's just something to show you that it's a more complex geometry than the simple box. So what we want to do is we want to now bring this geometry into Wasp, and we want to attach it to the part as an attribute. So what we're going to do is we're going to right-click on the skeleton attribute layer here. So the block 1 skeleton attribute, right-click, and go and choose Select Objects. So now all the objects that are on these layers are selected. We can now go back to Grasshopper. We can create a geometry component. We can right click and select set multiple geometries. To automatically store those geometries in a component. And if I go on and turn the preview back on, you see that my geometry is effectively in there. Now that I have this geometry stored in here, what I'm going to do is I'm going to use this geometry to create an attribute for my part. So I'm going to go to Elements, and I'm going to go to Wasp attribute. And whenever you create an attribute, you have to set 3 different values. The first attribute is a name that is going to be used to retrieve the attribute after aggregation. And so what I'm going to call this is I'm going to create once again a panel and call this skeleton. You need a value, which is what do you want to store in this attribute? And in this case is our geometries that we have here. And so we're going to put them in there in value. And lastly, you need a toggle to specify whether the attribute you're using is transformable or not. What does that mean? What does that mean is that any geometry that you have in Rhino, it's transformable, which means that if you move our base part from here to here, you also want to move the attribute with it. However, the attribute component can be used to store also types that are not geometric. So you could, for example, store a text. You could store a value. You could store a color. And so in those cases, those attributes are not transformable. And so you have to make sure that the transformable attribute is set to false. So in this case, we're going to set it to true and connect it to transformable. And we can now take our attribute and connect it to the attribute input. So we now stored an attribute in our part. And if we go on and reset our aggregation, you notice that it might take a little longer to compute. And that's because also all this geometry needs to be transformed after aggregation. But what we can now do is, if we come after our aggregation to our filter, so we filtered all the parts which are called block 1. What we can do is, instead of extracting the part geometry, we can go to Elements, and we can say get attribute by name. I'm going to connect my part. And I'm going to say that the attribute that I want is the attribute that is called skeleton. Again, as always, make sure if it's uppercase or lowercase, that is just the same. And so now you see it's going to take a while because the geometry is quite complex, but you see that what we have now here is our actual geometry. And what I can also do is I can right click and turn the preview of this off and then plug it in my custom preview instead of my block. So now you see that we have our complex unit being copied on all our blocks. What we want to do also is we want to do the same for our second part. So we're going to go to our second block. And I'm going to again go to Grasshopper, go to Rhino, sorry. Turn on the skeleton attribute of block 2. Which is a different design for the facade with some sort of little louvers. And so I'm going to right click again on the skeleton attribute and say select objects. So I'm going to have my whole unit selected. Going to go back in Grasshopper. and create a geometry component. And I'm going to right click, set one geometry. Sorry, oops, mistake. I'm going to go back, skeleton attribute, select objects, and then right click and say set multiple geometries. So I'm going to store the whole structure to it. I'm going to then create my same attribute in the same exact way. No, in a sense that you can do, so you have to always define them using this line for the components. So you always have to say that that has to be done. So what you can also do is that supports are kind of generic, meaning that they are looking for any type of part that are there. But what you can also do is you can use another component that is called adjacency and exclusions. And what those do is they allow you to specify also which component should be there. So then you could, for example, say on this face and this face, I always need both of these points to be covered. Otherwise, this will not be placed. But they're not implicitly defined. You always have to be defining them. So if, for example, you have multiple faces, you will always have to create all the possible combinations. So for example, these two, and then these two, and then these two, and then these two kind of thing. So it's not, let's say it's not defined like implicitly of two faces, also because it's a little bit hard to define really what a face is within Wasp. So you always have to specify where those are. So we imported our second block geometries. And so then you're going to go again and create an attribute. Again, I'm going to call it skeleton as well. I'm going to assign my value. And I'm going to create my toggle. Set it to true. And connect it to the transformable input. Then I'm going to take my attribute, plug it into attributes. And then I'm going to reset my aggregation. And I mean, you see that now things start to become a little bit slower. And it's not really a Wasp problem, but it's more a visualization problem because we're starting to visualize a lot of geometry. So I can now go to block 2, and I can just copy this one that is up here down and connect these parts, and then connect it there. And there you go. So now I have, for both of my elements, a set of custom geometries. And we have like our aggregation where you have these custom geometries. Yeah, so here we go. So, okay, I'll answer some questions. So let's continue first on the supports. So the supports are generally not that heavy to calculate because it's just a line mesh intersection. So you can actually have quite a lot of them and it would still be okay. So I would say the number of supports is not as impactful on the performance as the complexity of the part. So if you have a lot of supports on a very simple part, it's on a series of very simple parts, it's going to still be performing quite well. If you have also fewer supports, but on a very complex mesh with a lot of faces, that might take a lot of time. So for the other question, there was if it's possible to generate numerous aggregation. Yes. So it's possible. So the way you can do that is in the aggregation input, you have an input here that is called, so you saw that every time you press reset, sorry, I'm on the wrong screen. So every time you press reset, you get a new aggregation. And this aggregation is like randomly generated every time. However, you have here an input that is called the seed input. And this is allowing you to fix the random seed at a specific position. So for example, you're gonna say, for example, fix the seed to 50. Then that 50 will always create, till I don't change the seed, every time I reset, I'm gonna always create the same aggregation. So what you could actually do is you can just have like a slider that navigates the seed, and then you could run an optimization algorithm by changing the seed and every time creating a new aggregation. There is a tutorial on my YouTube channel. I think is the devlog #1, which is where I show how to do that. It's not perfect as an optimization because it's kind of a random search, but it's actually possible to do that. So you could actually run, I don't know, through 1,000 possible seeds and figure out the best aggregation in terms of your parameter. So making the aggregation follow a certain path, yes, it's possible. And that's when you're going to use something like a field-driven aggregation. So I haven't done this today because in 2 hours, it's a little bit complex and it takes a little bit too much time. But you can definitely go on YouTube and look for the field-driven aggregation tutorials. There's, I think the very first one is exactly how to make an aggregation follow a curve. For the scaling, no, like it's not possible because that's the way in which Wasp is built is exactly that it relies on parts staying the same. Because that's how it works. So if you start scaling parts, then like computation becomes really slow. You can modify parts after aggregation. And again, there's a tutorial somewhere, and I think I'm gonna make another tutorial about it quite soon. But you can look, there's wait, I can check what's it's called. So I forgot the name. So there's the devlog #8 on my YouTube channel that is called Rules from Aggregation. It shows you how to take an aggregation after it's built and go and modify it. All right, so let's maybe go on. We want to do one last thing, and then we can maybe go back, and if you have more questions and things, we can continue. But so right now we have this our aggregation, and we create our attributes that allows us to display this aggregation as it is. But let's now imagine for a second that we have an attribute that is a little bit more, let's say, smart. So what it means is, let's, for example, imagine, and we can take a look. If we go to Rhino under block 1 and you turn on smart attribute, you see that there's an attribute that here that is a little balcony. So of course, we could just attach this as an attribute as we did before and just aggregate. But what is the problem? The problem is that, of course, you don't want to have this attribute all the time. So for example, I might want to have it here, but then I might not want to have it here because there's another part connected to it. So what we want to see quickly is how to create an attribute that is, and that's how it's called, smart, in a sense that it's able to understand how is the connection configuration of the part defined and be displayed only if the right configuration is there. So what we're going to do is we're going to start by going to Rhino. I'm going to turn the block 1 smart attribute on. I'm going to right click, select objects as we did before. And I'm going to create a geometry component. And I'm going to say set multiple geometries and select all my balcony components. So now what we're going to do is we're going to create we're going to go to elements and we're going to create a smart attribute. So you see that the smart attribute is looking very similar to the attribute. Indeed, the first three inputs are exactly the same. But we have two more inputs. And what those inputs allow us to define is a configuration of the connection being occupied or not occupied in order to trigger our component to be displayed. So I'm going to give this an ID. And so I'm going to call it balcony, for example. I'm going to set my geometry as the value. I'm going to set again my toggle for transformable to true. And then what are the other two inputs? So the first input is which connections are influencing this, this component. And so the connections that will be influencing this component are the side connections. So the top and bottom, I don't care, but the side connections are the one that will influence it. So what I'm going to do is I'm going to go up to where I created my side connections for my part. And I'm going to take the connections and plug them in the connection input. So now that I plug the connections in there, I have now here 4 connections. And so remember that the way we created is that this is 0, this is 1, the back there is 2, and then 3. And what we have to do is we have to create a connection, what's called a connection mask. So what it means is that we have to specify 4 values, which can be either 1, 0, or -1. And it's going to be 1 for each of the connection, which is going to tell us if the connection has to be free, occupied, or ignored. So I'm going to create a panel. Oops, sorry. I'm going to right-click and uncheck multi-line data. And so remember, I know that I have this is connection 1, 0, 1, 2, 3. So what I know is that I need this connection to be free. So if I want a connection to be free, I'm going to type a 1. And then the other 3 connections, I don't care. So I'm going to just type a 0 for all of them. So now I have this mask that tells me that if I want this attribute to appear, I need to make sure that the block in the aggregation has to have connection 0 free. So for example, here it would appear. But for example, here it will not appear because the connection is occupied by another block. So we're going to connect this to connection mask. And we're going to then take our smart attribute, and we're keeping shift pressed. We're going to go and also plug it in the attribute input of our part. So if you're not working with my file, but you're working with your own file, you have to make sure that the attribute input is flattened. So if you haven't done that, please do so. So you right-click and select flatten. And we can now go back and once again reset our aggregation. So we have our new aggregation. And now we can go on and try to extract our element. So of course, you could just go and extract it in the same way by just using a get attribute by name. But in that case, we're going to get all of them. So you're going to get both the one that are valid and the one that are invalid. So what we're going to do instead is we're going to go to elements, and we're going to go to Wasp, get valid smart attributes. So we're going to bring that in. And now what's important here is that this input doesn't take the part as an input, but it takes the whole aggregation. And the reason for that is that it needs to know the whole aggregation in order to be able to check if the part is actually placeable. So we're going to connect our whole aggregation. And I remember I called this balcony. And if I now go and see, you see that my balconies are appearing wherever the the connection is not occupied. Of course, there's still elements in which they're going to collide. And that's because these elements are not connected, but they're too close to each other. And that's something that I'm going to be working in the future on and hopefully improving. But for now, you can see that still you have your balconies, which are always facing outwards, or anyway, even when they're not exactly outwards, like in this case, they're still in an open area of the aggregation. So I could, for example, take them and also plug them to the same display, or I could create a second display. I'm going to plug just this one and maybe give it a slightly lighter color. And so, yeah, so here you see how you can control these attributes that are a little bit more complex, so that they have some level of intelligence of being displayed or not displayed according to the aggregation. So I hope you could follow. If any of you got lost, what you can, of course, do is you can just go. And now that we finished everything, you can go and take the Wasp tutorial complete and bring it in. It's going to take a second. And there we go. So now in this tutorial, in this file, you also have another smart attribute. So we have a smart attribute on the second part. And you'll see that this smart attribute is a smart attribute that is this kind of overhang that goes around two corners. And so since it goes around two corners, it needs to have not just one connection free, but actually two of them. So you see that in this case, we have connection 1 and connection 2, which are set as 1, which means that they both have to be free for our overhang kind of pergola, so to say, to be displayed. So you see that that's then created in the same exact way. So yeah, so that was a little bit the idea. So you can see how you can go from something very simple, with very, very simple geometries, and gradually add complexity and more control to your aggregation in order to create more complex structures, and also how you can use attributes, and particularly smart attributes, in order to add more information that needs to be displayed just at specific locations in the aggregation. So I saw that there were a couple of other questions. So yeah, if you want to grow an aggregation on a geometry, it's possible. And as I said, once again, it's using field-driven aggregation. So as I said, I haven't done it because it's a little bit more complex. But you can check my YouTube channel, and there's tutorials that show you how to grow over a curve, over a surface, over a volume, and so on. Okay. Yeah, definitely. Yeah, I've seen the question from Theodore. Yeah, that's definitely what could be possible. You could also have, for example, different facades that appear when they have opening or not openings. You could create doors when two parts connect, and so on. And yeah, that's the idea. That's what this was really built for. So yeah, I mean, that was it from my side. So I hope you had fun. I hope it was clear. I might have been a bit fast, as I wanted to do quite a lot of things. But the good thing is that I guess you get also the YouTube video afterwards, and you have all the files, so you can always go back and look at it. And now, I mean, I guess we can have some questions or discussion if we have time, I guess.
Yeah, we do have time. Maybe if any students want to ask questions, you guys can maybe unmute yourselves and ask.
I'll turn my light on because it's a bit dark.
Yeah. maybe while we're waiting for some of the questions to kind of come up, I think this was a very interactive session. It was really insightful, and I think it was good to see how the new components are being developed also in Wasp. I guess while someone else is kind of looking at few questions, I was also wondering that what are your next steps with the tool? I know that you mentioned a lot of people have picked up the tool and you've kept it open source.
Mhm.
But are you also looking at some kind of responsive design in terms of environmental simulation and maybe using some of the other plugins and responding to what happens next with the aggregation? So are there any plans ahead for that?
Yes and no, in a sense that so I've done, like, just last week I posted a tutorial on Patreon on connecting Wasp to Ladybug.
Okay.
But most of the studies that I've done, and I've done also, I had students that did different kind of studies of linking it to structural simulations and different studies. But most of that had to do with, let's say, doing that pre-aggregation. So the idea was to do some sort of simulation and then find a way to convert the data from that simulation into a field of some sort, and then use that for aggregation. So that's what's there and what's possible. And of course, it's always a little bit of hacking of figuring out how to do that.
Yeah, I think a lot of post-processing as well. Then
yeah. And then, so that's one thing. The next thing that I think would make a lot of sense would instead to be able to either do that within aggregation, meaning like testing the aggregation as it grows and adapt it as it goes. Problem is that's kind of computationally quite heavy. But the main idea is that that's, let's say, the direction in which the development is going. So one of the last things that was added in Wasp is this aggregation graph, which is the possibility of visualizing the way in which the aggregation is built. And now that's, let's say, from the user perspective, now it's just an output, which is kind of nice to see, but doesn't have too much information. But in the background, what that is now allowing to have a more clear structure of the aggregation, so that you could actually imagine of like growing one branch, so to say, of till one step, and then kind of going back, modifying one part and adapting the branch. So that's one direction where that could be going. However, like, to fully implement this graph system into Wasp is a pretty big thing. From in terms of the, I mean, it's not huge, but it's big given the amount of time I have at the currently. So I'm not exactly sure what's going to happen. Another thing that I hope will happen, I had some discussions with some people, but that's still very, very early, is that it might be that in some time in the future, there might be a Wasp for Blender, which could be quite interesting, moving even more into the whole open source kind of community. So those are the main things that are, I would say, there. One thing that I've been developing and that is not yet fully published is since right now I'm really working a lot with the robotic fabrication. There has been quite a bit of development on that side. So for example, being able to, while aggregating, already check if a block can be placed by a robot or not, and kind of add that information in there.
Yeah, I think that would be quite cutting edge to kind of do it in real time, and while fabrication is also kind of happening. Yeah, that kind of looks future forward now. Yeah. Well, good luck with that. Are there any questions from YouTube, Amit, which we can kind of address? Okay. I think yes, it was quite structured as a tutorial, and I would just kind of say a formal thank you for your time. I've tried to post your channel as well as many other links that you have shared. We'll create a GitHub repository also for all the students who are curious onto the files and are looking forward to the files that are being shared. And just as a last kind of closing to the session, we are going to have a session tomorrow, which will be again our continued series of philosophy session. I'll just share my screen here. Yes. So again tomorrow we'll have another session which is on architecture and philosophy. Professor Neil Litch will be moderating the session. The session is on the works of Judith Butler, and the panel will be with Helen Ranting and Amelia Jones. And on 8th of December, we are hosting the session called Resourceful Architecture. And this session is going to look at sustainable futures. So please tune into to the session. This will be live streamed on our YouTube page. And that's all for today. If we do not have more questions, I think yes, we've got a lot of compliments over there for you, Andrea. Yes.
Thanks everyone for taking the time. I hope it was fun. And
it was amazing. Yeah, thank you.
Great. Thanks. Nice. Yeah, and as I said, so I just shared some links already with you guys. So just check out the YouTube, check out Patreon. You can find a lot of information more on like the things I couldn't show today in 2 hours, because well, 2 hours is not a huge amount of time. So yeah.
Okay. Thank you.
Okay. Thanks everyone. Yeah. Oh, hi Mark. Nice to see one of my Patreons there. Cool. Thanks everyone. So I could share the files one more time so that you guys have them maybe. So yeah, thanks everyone. Bye.
Bye-bye.